Begin with a word of prayer. So, dear Heavenly Father, we thank you for today. Thank you for these students. Just pray that you'd guide my thoughts today. Help us just understand a little bit more about this thing called Fourier Series. Lord, in your name I pray. Amen. So, the concept of a Fourier series is as follows. So, I'll give you a little bit of history here. So, what I'm following is it's an additional section from Stewart's calculus. I like it. It's right at the right level for calculus 2. And the reason I like this lecture for you guys is it's just an interesting new thing. It has tremendous physical applications, and it also gives us a chance to do some difficult integrals. And so the concept of a Fourier series basically goes back to Fourier, who was solving something called the heat equation. All right, so what he found is that an exponential times a sine solves the heat equation. All right, and the thing is, you might imagine the temperature on some sort of bar being some sort of initial temperature distribution. All right, so the temperature at each position in the bar is given. So he said, well, I should be able to, and the thing is, the solutions to this wave equation, there's not just one solution to it, there's infinite number of them for different choices of n, like sine of 3x, sine of 2x, sine of 4x, sine of 5x times exponentials of a particular type. Well, the thing is, if you plug in times 0, the exponentials go away, and you're just left with this sort of sum of sine functions. And so, assuming that makes sense. And he said, well, if I could take the initial condition function for the temperature distribution and also expand it in terms of sines, then I could match the solutions up, and I'd have a solution to the wave equation, which is a partial differential equation. And so, but that was a giant leap around, I think it was early 19th century when he did this. I forget, 1806, 1820, somewhere in there. So he just proposed that you could take pretty much any old function and expand it as a sum of sines and cosines. So a sum of sines and cosines is a Fourier series in the same way that power series is a sum of x to the n. So I'll start out by just giving you sort of the generic one, and then we'll figure out how it works. So here's a typical one. Looks like this. F of x equals to a sub naught plus a sum, n equals 1 to infinity, a sub n cosine of nx plus b sub n sine nx. So our approach here, so what this means, of course, is, you guys know how this notation works. This is a sub 0 plus a1 cosine x plus b1 sine x, and so forth and so on, right? It's this infinite series of sine and cosine functions. So he says we start by assuming the trigonometric series converges and has continuous function f of x as its sum on the interval. So we're just going to, as a starting point, assume this converges to continuous f of x on minus pi less than or equal to x less than or equal to pi. And so, you know how Taylor series work, right? You remember? So just we're at the moment we want to kind of do the analog of that. So just a reminder, if I have f of x equals to 3 plus x minus 1 squared plus 13 times x minus 1 to the 50th, right? What can you tell me about the function given this Taylor series centered at 1? What does it tell you? There's tons of data here, right? Some low-lying fruit. F of 1 is 3, right? F prime of 1 is 0. F prime prime of 1 is 2, right? The coefficient here, so this we could compare to 1 over 50 factorial times the 50th derivative at 1 of the function, right? times x minus 1 to the 50th, of course. So I mean, we can compare the coefficient here to this, right? And that would tell me the 50th derivative at 1 is equal to what? (13 times 50 factorial, right? So we've done calculations like this, right? So the question is, and you know the rest of them, right? Otherwise, what do we get? Right? So for n not equal to 0, 1, 2, or 50, it's well, I guess we don't know. From what's written, all I can do is this is for, actually all I know is this, right? Or more precisely, for n equals 0 to 49, 0, 2 not included. Okay? So the question then is, if that's the connection of the coefficient of the Taylor series, it relates to the derivative by Taylor's theorem, right? Well, how do we figure out these Fourier coefficients? How do you figure out what a sub naught is, a sub n is, b sub n is? Like, what are those in this thing? So what he does, again, this is a supplement to Stuart. I'll post a link for you guys. It's freely available, I think, on Stuart's website. If I can't find a link, I'll post it to Blackboard. You shouldn't mind. That joke is in slightly bad taste. All right. Yeah, he's left. He's left the land of the living. Let's see here. Why are they so loud? You know, usually I would just let it go, but I'm annoyed today. Could you guys go talk somewhere else, please? Can you go talk somewhere else? Thank you. All right. Let's see here. So he says, what happens if you integrate from minus pi to pi f of x dx? What happens there? So I'd like to use some thinking here. So assuming we can integrate term by term, what happens to the series, the Fourier series? What happens when you integrate sine or cosine of any multiple of x over a whole cycle? 0, right? Like sine integrated from minus pi to pi, or cosine integrated from minus pi to pi. This is it's ended up being some integer multiple of full cycles of sine and cosine. So these would integrate to 0. And so when I plug in that series over in here, right? Oh man, I wasn't going to write it out. That's too late. I was trying to chill here. This is not helping my chilling. So this is 0. This is 0 because of it integrates to 0. Assuming that you can integrate term by term. And long story short, we just get 2 pi a naught, right? Because a naught's a constant. And lo and behold, we have a formula for a naught, right? Therefore, a naught 1 over 2 pi integral minus pi to pi f of x dx. So the constant coefficient apparently has to do with the integration over some region of a function which is given, right? Well, okay, so this is, this is kind of the same kind of song and dance we do with the Taylor series, right? On the one hand, you want to consider a power series, which is sort of abstractly defined by the power series. On the other hand, you want to consider a function which is given by some other logical means. And then you want to discover, if I want to model that function by a Fourier series, what conditions do I need? How do I pick coefficients to make that Fourier series model the function? So if I'm given f of x and I want to make it reproduce if I want to reproduce it with a Fourier series, the constant over minus pi to pi, the constant coefficient I need to choose to be 1 over 2 pi times the integral of the function over the interval. What's that? what I'm saying is, imagine f of x is not just defined. I mean, okay, so maybe I need to use a different letter. I mean, so given g of x, to find a naught, an, bn, etc., such that g of x is equal to a naught plus, so forth and so on, I choose a naught equal to 1 over 2 pi integral of g of x dx minus pi to pi. Right. In other words, if the function is given by that formula, it forces this connection on the constant coefficient. So again, suppose the function is given by Fourier series. How do we figure out what the a sub n and b sub n are? Well, here's a theorem of calculus for you. The integral from minus pi to pi of the cosine of nx, all right, times the cosine of, let's say, jx dx is equal to what? Do you remember the, you might remember the identities. Save me some work.
I think there's 2 cases.
Yeah, there are 2 cases, yes.
0 and different than J.
Oh, I don't want the answer. I want to know how to calculate it.
Oh,
sorry.
maybe use the ix.
Oh, okay. Yeah, you'll make me work. Very good. Again, you're not helping my chilling. Let's see here, cosine jx. Yeah, I can do it that way. I was hoping you would tell me the end result of this. Well, I want. Yeah, okay. Admittedly, I'm very greedy. I don't want the answer, and I don't want the initial part of the full calculation. I wanted like the midway point, so it would look like I did something. I'm asking for there's a trig identity that we can rewrite this cosine of a product in terms of a sum of cosines. And I mean, we'll find it in just a second here. This is 1/2 e to the n plus j I times x plus e to the minus I n plus j x plus 1/2 e to the I n minus j plus e to the minus I n minus j x. All of that divided by 2. In short, there's this identity. This is really the integral from minus pi to pi of 1/2 cosine of n plus j plus the cosine of n minus j. You sure you want to take my Calc 3 next semester? Let's see here. Your schedule is, you're stuck with me, huh? Okay, yeah. That's good. It's 8:15, so whenever I make a mistake, you can fix it for me. That's good. I'll make lots of mistakes to make sure you're paying attention. Just for you. That's here. It's funny, when my wife, she also has a degree in math, and she takes that complex analysis. She has a master's in math. It's funny, like the professors would be like, what did I do? Because you just look at her and she's like, there's something wrong with what you did. Pretty much. So it's very convenient to have students who can correct mistakes, because I hate finding out mistakes later. Anyway, so thank you.
I appreciate teachers that are okay with their mistakes being pointed out and just take it as good. People never write the truth. I don't like teachers that just do it.
Yeah.
Everyone makes mistakes. It's just,
Yeah. Well. Yeah. All right, so minus pi to pi. Now, this calculation assumed something just now, right? I divided by n minus j, right? So this is for n not equal to j. The calculation I'm doing at the moment. And what happens? You've got sine then of multiples of pi. So this is 0. So basically, we have this being 0 for n not equal to j. Let's see here. Yeah, what happens when we have, on the other hand, minus pi to pi, cosine nx, what happens? We get cosine squared nx, right? Of course, I could use the identity again and just make my life easier, right? Why don't I do that? So it's 1/2 what? Cosine of 2nx, right? Plus 1. This integrates to 0, and that integrates to what? Pi, right? Okay, so what's the point? By the way, similarly, you can prove that the integral from minus pi to pi of the sine of nx times the sine of kx, guess what, dx, 0 for n not equal to k, and pi for n equal to not equal to k, n equal to k, right? And then there's one other case to consider. Similar, and the calculation of these is very similar to the one we just did, so I won't do it, but also the integral from minus pi to pi of the sine of nx times the cosine of kx dx, well, that's just 0. So with these three fundamental identities and a little bit of courage, we can calculate the components. See, because what we do is we just take the Fourier series and we integrate. We multiply it by a sine or cosine and integrate, and that will select the coefficient. Let me go through it. If we integrate f of x times the cosine of kx dx from minus pi to pi, what happens? Let's see here, f of x was what? So I'm going to go ahead and multiply this cosine through the Fourier series, okay? So like I get a naught times the cosine of kx, right? Plus the sum. And I'm going to go ahead and bring this, I'm going to bring the integration inside too, if you don't mind. Integration from minus pi to pi. And the coefficient we can leave out here. A sub n, right? And we've got ourselves a cosine nx, cosine kx dx, plus the sum n equals 1 to infinity, a b sub n integral from minus pi to pi, sine of nx, right? Cosine kx. Do you guys see what I did? All I did was I took the Fourier series, I multiplied by cosine kx, and then I integrated both sides. And then I assumed that I can integrate term by term. So most of this stuff is 0, right? There's a dx missing, but 0. This integrates to 0 always. And this, what happens here? You could say that this is really pi times what's called the Kronecker delta of n comma k. Kronecker delta is a really cool thing. Kronecker delta n comma k is equal to 0 for n not equal to k, and it's equal to 1 for n equals to k. That's the way this symbol works. Very useful combinatoric device. Now, basically, that's the natural enemy to the infinite sum. It basically collapses the sum to a single term. Everything is 0 there except for one thing, right? So this is just equal to pi times a sub k. which is pretty awesome because we just found the formula for a sub k. A sub k then is equal to 1 over pi integral from minus pi to pi of f of x times the cosine of kx dx. Through a nearly identical calculation, if you multiply the Fourier series by sine of kx, what happens? The cosine terms drop out, and you just pick up the n equals to k part and the sine coefficient. So we get the same formula for the b sub k. B sub k, 1 over pi, integral from minus pi to pi, f of x, sine of kx. So these are the so-called Fourier integrals. Now, of course, I don't like k. I like an n there, so let me erase that and change them to n's just for my future convenience, if you don't mind. Standard example work for you guys. Yeah. Basically, I just want to work 2 examples in here. Then we'll be done. So this is example 1. So here we have f of x equal to 0 if minus pi is less than or equal to x is less than 0, and 1 if 0 is less than or equal to x is less than or equal to pi. Oh, less than pi, fine. All right, and f of x plus 2 pi is equal to f of x. So he's giving us what's called the square wave. Right, if you graph this thing, it looks like 0, right? Over here to 1, over to pi rather. Oh, I'm sorry. Actually, I'll fix it just a second here. Sorry, I'm an idiot. Anyway, so this goes on. And the reason it's called the square wave, of course, is because usually we can't help ourselves but to draw these little dotted lines, that aren't technically part of the graph, but then you can see why it's called the square wave, right? And so forth and so on. Right. So you can find a Fourier series which models this exactly. So, what's that?
Which is just weird.
Is it? Right. I think that's why when I know, I think it's why it's kind of shocking that Fourier said that. He wasn't the first person to suggest this. People have thought about building things from sines and cosines before him, like Euler, shock, Lagrange. Yeah, stupid Euler. I hate him. No, I'm sorry. So let's figure it out. We got to do some integration, right? It's not too bad. So a sub 0, we need a what? 1 over 2 pi, is it? I forget. I erased it, didn't I? Dope. Yeah, 1 over 2 pi.
Yeah.
Integrate from minus pi to pi, f of x dx. Now what is that? That's actually 1 over 2 pi. How's this work? I mean, it's really just the integral from 0 to pi, right? And f of x is just 1 there, you know? So what do we get? Yeah, just pi. Excuse me, pi over, yeah, the integration's pi, but then it's pi over 2 pi. So like you said, it's a half. All right, how about the a sub n? Now we've got f of x times the sine of nx, right? Okay, so that's really what? 1 over pi, the integral from minus pi to pi, 0 to pi, right, of sine of nx, yeah. So we can do that integral, right? So we've got, what is it, 1 over n? Well, minus 1 over n, right, cosine of nx. Let's see here, so what do we get? So it's 1 over n, cosine of n pi, right? Oh, there's a minus, isn't there? And then plus 1 over n, right? Now if you look at that, that's 1 over pi times, excuse me, it's 1 over pi n, right? 1 over pi n times 1 minus 1 to the n. See, because cosine of n pi is minus 1 to the n. And so this is what, I mean, this case-wise, you can say something here. This is either, I'll do it here. So this is either what? This is either 1 over, I'm trying to think here. If n is even, we're in trouble, right? So if n is even, it's 0. But on the other hand, it's 1 over 2k plus 1 times pi. And then this just simplifies to what? If n is odd, that becomes 2, right? So it's this for n equal to 2k plus 1. Let's calculate the other one. B sub n, 1 over pi. Oh, wait a minute. Did I just... Is this why you're looking... You looked disgruntled. For good reason. I have swapped the meaning of a sub n and b sub n. Yay! So this is b sub n we just calculated. Okay, fixed it. Fortunately in time. Here's a sub n. So a sub n we multiply by cosine, right? Is the thing. All right. So this thing we're doing right now is called the full Fourier series, for what it's worth. So what do we got? We got 1 over pi n sine of nx, right? Oh, but that's easier. Yay. All right, so then what? Now we can construct a Fourier series, right? So put this together, we get that f of x is equal to a sum k equals 0 to infinity of 2 over 2k plus 1 pi times the sine of 2k plus 1 x. Oh, and I forgot something. Something very, very important. Yeah, 1/2. So let me write out the first few terms. You've got 1/2 plus, how's it go, 2 over pi sine x plus 2 over 3 pi sine 3x plus 2 over 5 pi sine of 5x plus da da da. You can kind of visualize how this goes, right? Let me hazard a picture here. So here's a half, right? So, I mean, first of all, the zeroth Fourier polynomial, if you will, is just kind of dumb, right? It's just a line and a half, which is, I mean, okay, it's the average of the function, isn't it? That's what that means, right? Something like that. So then what is 2 over pi is what? It's like 0.6, 2/3 basically, a little bit, somewhere around there. And so that, it's a little bit shy of, it's going to overshoot a little bit, right? And so that's something like, let's see if I can do it right. So there's like the first two terms, something like that. What happens if you add the 3? Then it gets, there's 3, three signs, three signs in there. So that would look something more like, and I won't do it justice. Let me try it here. So it's supposed to go 0. I mean, the sign of this, and this has a smaller amplitude, right? The sine of 3x is 2 over 3 pi, which is like 2/9. So that's only about 0.2-ish, right? So when it's at its biggest, it's, I can't do it justice very much, but I don't know, it does follow. I mean, I don't know. I don't know. I can't do it. It's above my skill graphing. But I'd have to get the computer out and do it. But maybe I should do that. I don't know. If I have time. Oh my goodness, no, I don't. Curses. All right, let me get to the point. I would encourage you, though, if you do have time, just to play with a graphing calculator, just add these, and you'll see that you get closer and closer and closer to the square wave as you add more and more of them. It's very cool. Now, a lot of times you want to look at like f of t, or let's say g of t, for minus L less than or equal to t less than or equal to L. Instead of being stuck with minus pi to pi, you might want to go from L to minus L. So you can achieve that by making a substitution. What do? If you want, x, what do? You put x equal to what? X equal to, how about, pi t divided by L, right? Or t is equal to what? Lx over pi for the other way around. Anyway, you make that substitution in these integrations, and it gives you the formulas for expanding a function with respect to a period other than minus pi to pi. And I want to write the formulas down for it. Just give me a second here, I'll write them down. By the way, fun fact, the Fourier series, it converges to the halfway point on jump discontinuities. Like the Fourier series, when you add in infinitely many terms, it will take on the value of half any of the jump points. And then otherwise it will converge at points where it's continuous. But dang it, where's my eraser? Ah. All right, so so if you want x to go between minus L and L, the way the formula changes is instead of having n pi, you have n pi x over L, n pi x over L. So you see what happens here is when you put L equal to pi, these formulas simplify the nicest way possible, right? See how that is? So the choice L equals to pi is a very nice thing to start with because it makes the formulas most beautiful. But just by making a substitution in our earlier work, we can derive that a sub naught in this case is 1 over 2L, integral from minus L to L, f of x dx, and the a sub n, 1 over L, integral from minus L to L, of f of x times the cosine of n pi x over L dx. And I think you might be not too surprised when I write b sub n is 1 over L, integral from minus L to L, f of x times the sine of n pi x over L. Okay. Now there's a Fourier convergence theorem, and it simply states this. I'll read it for you. If f is a periodic function with period 2 pi, and f prime are piecewise continuous on minus pi to pi, then the Fourier series is convergent, and the sum of the Fourier series is equal to f of x at all numbers where f is continuous, and at any points where f is discontinuous, it converges to the halfway point of its right and left limits at the point of discontinuity. This is the Fourier convergence theorem. There are much more to say, okay, but I think I've more or less proved this in one of my other classes, my 495 classes that meets Monday, Friday this semester. I think we worked this out. It wasn't too bad, actually. I think, well, we may have cheated, though. I don't know. This is the sort of thing that ideally would be proved in like the latter half of a real analysis class or something. But I think typically real analysis classes tend to get focused on more esoteric things than these kind of. All right, getting to it then. So this is how you do it for a non-pi to pi. So an interesting example. So by the way, this is actually how we hear sound. So like your ear, as something like inside your ear, there's something like there's this thing with lots and lots of hairs, and basically every hair, like there's a hair of different lengths, and the different lengths resonate to different frequencies, and this is a sum over different frequencies, actually. And so the way it works basically is your ear picks up on the coefficients, the a sub n's and the b sub n's, and decomposes sound into, in some sense, into this list of numbers that are Fourier coefficients, and that, in some sense, is how our brain processes sound. Something like that. And there's MP3s, but whatever. But I think your brain is more exciting. Also a fascinating example of evolution. But anyway. Yeah, whatever. So here is a specific one, and so application to the x squared function. So if you look about x squared from minus 1 to 1, what's it look like? It's even, right? So if you were to extend it periodically, it would look like this, right? So what would the Fourier series, and so on, so forth and so on. So what would the Fourier series for this look like? I mean, basically all I have to do to calculate the Fourier series for x squared on minus 1 to 1 is I just have to plug in x squared in here and do these integrals. Now this is what I was hoping I had time for today, but I just don't. See that we would have got to integrate by parts cosine times x squared 2 times, and we would have got to integrate x squared times sine 2 times, and then there's an n and a pi floating around. It's quite a beautiful integration, a completely legitimate calculus 2 final exam question. That's what I was getting to. So you can calculate, and it can be shown. Oh, this one's easy. Of course, the integral L is equal to 1 here, right? So 1 over 2, integral from minus 1 to 1. I think this one you could do, right? X squared dx equals to what? I'll do this one. Thanks a lot. You should be like, well, that's really magnanimous of you. This is what? 1/2 times 2/3, right? Also known as a third. Okay. You want that one on the final? Yeah. I think I might enjoy grading that on the final, actually. But it turns out that a sub n, which of course is 1 over 1, which is just 1. Let me not write that. Integration from minus 1 to 1 of x squared times the cosine of n pi x. And this is also nice. L equal to 1 is also nice because you have n pi x. You don't have like n pi x over 3 or something stupid. So at least it's just n pi x dx. Anyway, you do this integration, and it works out to minus 1 to the n times 4 divided by n squared pi squared. So therefore, we find the result that x squared is equal to 1/3 plus the sum n equals 1 to infinity minus 1 to the n times 4 divided by n squared pi squared times the cosine of n pi x. By the way, the b sub n's are 0. That's geometrically obvious because the b sub n is picking up on the odd part of the function. This is an even function, so it has no odd coefficients, like the sine picks up odd pieces. And this integration simplifies to integration from 0 to 1, right? Because cosine is even and x squared is even, so this integration. And then basically when you integrate by parts 2 times, you pick up stuff with like sine of n pi x or x times sine of n pi x. Those things drop out, and the only thing that survives is just that one term. Anyway, it would take us about 10 minutes to do the integral, but I want to get something from this. Now, we believe the Fourier convergence theorem. It says that the Fourier series converges to the function everywhere the function's continuous and to the halfway point at discontinuities. There is no discontinuity in this one, so it just straight up converges to the x squared repeated function. In particular, it would converge at minus 1. What happens when we put x equal to, oh, excuse me, how about put x equal to 1? What happens when you put x equal to 1? Right, because cosine of n pi is minus 1 to the n. So these cancel. What do you get? You get 2/3 is equal to the sum, n equals 1 to infinity, of 4 over pi squared, 1 over n squared, which gives me then the sum, n equals 1 to infinity, of 1 over n squared equals to what? 2/3 times pi squared over 4, also known as pi squared over 6. And there you go, guys. I claimed that earlier this semester. Here's why it's true. You can derive other non-obvious series with this method, yeah. This opens up a whole new vista of results that are not available with the methods of calculus we know otherwise. Yeah.
X cubed is odds that you drop all the cosine and pick up all the sine.
Yeah, I mean, there are other things here, right? Like if you put x equal to minus 1, Oh no, that doesn't do anything. Maybe if you put x equal to, maybe if you put like x equal to a half or something, that would do. I mean, there's other things in here like sums of odd squares but yeah, there's of course much more to do. Like here his problem 18 has a thing for pi squared over 8 being the sum of the odd squares, sum of the reciprocal of odd squares. Or he's got another one that's like the alternating. Anyway, there's tons and tons and tons of other things. But I just think this is neat. Euler somehow knew this in like 1737. But I don't know how. Because he's Euler, yeah, probably. But yeah. I'm sorry, I seem to have gone over time, but I'll shut up. So you can turn it off.